sometimes we want to know how fast something is going, bam, at an exact instant. For example, in your car, it doesn't tell you how fast your average speed was. It tells you how fast you're going, bam, at that instant, at that specific point of time. So today we're going to talk about how to calculate instantaneous speed. So I want to move to a PowerPoint. Okay, in this slide here, we have a blue man driving in a blue smart car. Now, you guys have all heard of the blue men?
Yeah.
Yes?
Yes, we have.
Has anyone here not heard of the blue men?
You mean like the Blue Man Group, right?
The blue men group, yes. Sometimes people haven't heard about them, so I show a little clip while you guys are working out these calculations here. I'll show the clip anyhow. Basically, folks, what I want you to do is sketch this out right here, where it's a highway and there's mile markers, the 100-mile marker, the 200-mile marker, the 300-mile marker, 400, 500-mile marker. Most highways have little markers on the side of the road saying like how many miles you've gone, or which mile marker you're at. This blue man here notices the time at the various mile markers. It's 2 o'clock at point A. It's 4 o'clock at point B. 5:45 at point C. 7 o'clock at point D. 8 o'clock at point E. What I would like you to do is calculate the average speed from B to E, and then from C to E, and then from D to E in miles per hour. Now you want to be a little bit careful because these times up here are given in hours and minutes. So you want to change it so that it's all in hours. For example, if you went 1 hour and 30 minutes, 1 hour, 30 minutes, how many hours would that be? 1.5 hours. So you got to keep that in the back of your mind. Now, basically, you want to just sketch out the diagram and then figure out those 3 average speeds. If you want to show proper problem format, you could show it for one of the calculations, but you don't want to show it for all 3. That's redundant. That's just too much grunt work. So basically, a lot of times, it's very convenient and well accepted to just write down the answers, except for one of them, show a sample calculation. So you don't have to keep writing the same things over and over again. So the car takes off. There it goes.
Wow. It's awesome.
Anyone want to speculate what that X is for between D and E?
You want to know the speed at that exact moment?
Yes, we're going to be talking about the speed at that exact moment. Bravo. And we're going to be making the transition from these average speed calculations to the instantaneous speed at point X.
plug it in?
and just put the answer down.
Just the alright, cool.
Right. And you could label like this over here and just say like sample calculation.
I forgot what to do when you get eating the speed.
Huh?
Well,
Well, in physics we don't put a bar over it because we want to indicate precision. Everything's measurement, so you want to round to the correct number of sig figs. Here it's kind of hard. I mean, the mile markers have 3 sig figs, but the times are like to the nearest minute. So, you know,
If you convert that into hours, can
We
you
show that
also
conversion.
encode it like 3 sig figs also?
probably.
So then that just means the lowest number of 3 sig figs is 3, so you just use that.
I would just use that, yeah.
So 3
Can we show the conversion like in the interval of 2 hours 15 minutes to 2.25 hours?
You could, okay, but you don't have to in this case. But if you know how to show that, wonderful.
I have a calculator.
All right, while some people are finishing their calculations, I wanted to go back and show you that Blue Man video here.
Wait, what was the code?
Your attention, please. Thank you for choosing Earth as your planetary vehicle. We hope you enjoy the many wonderful features of this planet as you hurtle through the cosmos. Please note, however, that in the event of continued inaction in the face of global warming, your seat cushion can be used as a flotation device. Also, please take a moment to locate this planet's emergency exits. As you can see, there aren't any. Earth to America. Can you hear? Sending out a message. Loud and clear. Can you hear?
September 21st is a Sunday, and I think it's going to be the largest march on record, on global warming and what can be done about it. Many, many organizations are participating. The Sierra Club, which I'm a member of, they've been sending me emails that they're going to be part. It's supposed to be a very peaceful march. It's right before the United Nations are gathering to work out some new trade agreements, which a lot of people feel might be harmful to the environment. So if that's something you're into, you might want to Google it, check it out, talk to your family about it, and go. Okay, so when you calculate average speed, it's very easy. The average speed is the rate at which distance is covered, and by definition, we know the formula to calculate the average speed. Just use this formula. Average speed equals the change in position divided by the change in time. We don't usually write out those delta signs, but really it's how much the distance changes compared to how much the time changes. 75 miles per hour. C to E, 89 miles per hour. D to E, 100 miles per hour. Now that doesn't necessarily mean it was going that fast at any of those points. But here's the thing. If we were going to use one of those three calculations as a best estimate for instantaneous speed, which average speed best indicates how fast the car is going at point X? B to E, C to E, or D to E? It's just an estimate. But when we figured out the average speed from B to E, did that give the best estimate for how fast it's going at point X? Or was it C to E? Or was it D to E? Johnny?
It was DT because the 2 points that are being calculated is the closest to point X.
Exactly. And if we could narrow in that time even closer, the smaller the amount of time, the closer the average speed calculation is to the instant speed at that particular point. So if we narrow it in even closer and said, oh, what about between this time and that time? That would even be a better estimate. So this one right here is the best indicator of how fast the car is going at point X. The smaller the time interval, the better the estimate is to the instantaneous speed. The thing is, we know that average velocity is equal to the change in distance. I'm sorry, average speed is equal to the change in distance over the change in time. But if you're just analyzing one single point at one instant of time, what's the change in time?
None.
0. It's undefined. So one thing you do is a limit. And you'll learn more about that when you take pre-calc and calculus, and maybe physics C. So let's lay it out. How can we calculate the instantaneous speed at this point X? And there's 3 ways. Number 1, we can approximate the instantaneous speed. We can approximate the instantaneous speed by using the good old average speed formula. But if we're going to do that, what's up with the time interval we want to use? Richie?
The time interval has to be really, really small.
The time interval has to be really, really small. The smaller the time interval, the better the estimate. Isaac Newton called it a infinitesimally small time interval. Small. Even your car speedometer does an average speed calculation to estimate the instantaneous speed. There's a little sensor on the side of one of the wheels, and it times how long it takes the wheel to go around once, which isn't much time. And what other piece of information would would the car's computer need to know if it's going to calculate the instantaneous speed? If it knows how much time the tire goes around once, Richie?
The biggest diameter of the tire or
Well, if you know the diameter of the tire, you would be able to get something else, but what does it really boil down to? What other measurement on the tire? The circumference of the tire, yeah. And if you know the circumference of the tire, that's the distance the car went forward in that much time, and it does a little baby distance over time calculation, calculates that average speed, and then says, that's how fast you're going that instant. And then it does it over and over and over again. So it's estimating your instantaneous speed by telling you your average speed for each tire rotation. I don't know if anyone knows Mr. Sontag. He has a really nice Jeep Wrangler, and he purchased like big balloon tires, so the Jeep sat up high. But the car's computer module didn't know he put these bigger tires on. So guess what ended up happening? What happened to the circumference?
It increased, so he ended up going a lot faster than it said it was going.
Exactly. The circumference was a larger circumference. So now he was going faster than his speedometer indicated. And he got pulled over, and he thought he was doing like, 45 miles per hour, and he was really doing like 55 miles per hour.
Oh wow.
Why does that happen?
Because the car uses the circumference of the tire and divides it by how much time it takes the tire to go around once.
Okay.
And if you put bigger tires on,
It's a different tire.
it's a different tire, the car goes forward a longer ways in one rotation. But the car's computer only thinks it went the original distance when it went actually farther.
Is every like thing in the tire the same? Because how did that big of a tire fit in? Is the rims all the same?
Well, the inside rim and where the holes are, that's the same.
That's
Yeah.
alright.
Yes.
How a radar gun measures instantaneous speed? Like, how does it do?
That's an excellent, excellent question. And we're actually going to use a sonar gun eventually in lab. And basically, what the radar gun does, which is similar to what the sonar gun, let me explain it in terms of the sound gun, the sonar. The sound gun, say I have a little sound gun like this, it sends out a little sound signal. Imagine a little tick sound, tick. And when the sound signal hits the car, it echoes back and goes back to the gun. Now, the computer module with that sound gun knows how fast the sound is traveling. So, if it knows how fast the sound is traveling,
Hello.
if the sound comes back lickety-split, what does that say about the location of the car?
It's close.
It's closer. If it takes a longer time for it to come back, it's farther away. So the sonar gun can determine the location of the car depending on how much time it takes the echo to come back. And then it does it a moment later and figures out where the location is, a few milliseconds later. And if it knows where it was in the first place, by sending out that little thing and figuring out the location, and it knows where it is in the second place, guess what it can figure out? The average speed in between those time intervals. But the police officers don't use a sonar gun like we're going to use in lab. They use a radar gun where they shine invisible light, and the invisible light reflects off of the car, radar waves, and that gun catches the reflected light rays. And if it takes a long time for the light to come back, the module knows that the car's located far away. Daniel.
Does that take into account like air density?
It probably does because they have to know the exact speed of the light to determine the locations. So it probably does. And the air isn't really going to slow down the light.
No, I mean like on a sonar gun.
Oh, it probably just uses The ones that we have probably just uses the speed of sound at standard temperature and pressure. So if there was a fluctuation, it probably would be like miscalculated. You know, calibration would be wrong. Never thought about it. That's pretty interesting.
How can like, you know those guns that can tell how fast you're going? Like, how can they tell how many like miles per hour you're going? Like, how does that work?
Well, that's what we were just talking about.
No, but like, isn't that like where the object would be after? Oh,
Okay, so if it knows where the object would be 1 second, and then it does it again, and it knows where the object is in the second second, if you know where the car is at one moment, and you know where it is at the next moment, and you know how much time is in between those two, you can figure
yeah,
it
but
out.
aren't there guns where you can just like like the ones that like police officers have? You know what I mean?
That's what I say. It does the calculations for you.
Oh, it does.
It still
Oh yeah, it does it all quick.
Oh, okay. That's cool.
Yeah,
I didn't know it does it for you.
it just does it for it, and they get a readout.
That's really cool.
Yeah.
That's
Yep.
cool. That is
You could also calculate the speed because if you're sending out one wave after another, the rate at which the waves echo back, which is known as the frequency also shifts, and we're going to talk more about that when we learn about the Doppler effect with sound waves. So there's another way of thinking about it as well. All right, so the second way to calculate the instantaneous speed is by graphing the distance time data and then drawing what is known as the tangent line. And then the slope of the tangent line turns out to be exactly equal to the speed of the object at that instant.
How would you do that?
And we're going to learn more about this when we do the second part of that graphing packet. So for now, you're just copying this down in your notebook, but more to come about the meaning of this.
Quick question on that.
Yes?
If you're graphing, like if you're drawing a line tangent to the curve, then wouldn't the parameters for the curve that you're drawing also should have a small time frame? Because if you don't have a small time frame, like there will be inconsistencies in the graph that you're drawing. Like,
Well, the smaller intervals between measurements, the better.
okay.
The better. Last but not least, folks, a third way to get the instantaneous speed, which somebody mentioned right at the beginning of class, is to use limits and ultimately take the derivative. And, whoopsie. And if you go on to take calculus and AP Physics C, you'll learn all about that. This is beyond our class. We're not going to be doing that in this class. But just to give you like a, this is ultimately how it would be done. So the average speed, very easy to calculate. Change in distance over change in time. Instantaneous speed can either be approximated, done on the graph by drawing the tangent line, or by using calculus. Take a break, come on back. We'll be doing our lab now. Give me 1 second.
When did we have lesson 9?
That's that sheet we did yesterday?
Are you still alive?